welcome the participants here to our 10th EFCE Spotlight seminar on important topics of chemical engineering of these times. You may have seen we have another one. You have a second chance if this is your first time you'd participate tomorrow on quality by design, but we've already talked about things like chemical reaction engineering, mechanics of particulate solids, or education of chemical engineers. And I'm very proud of this Spotlight series, and particularly of the colleagues in the working parties and sections of EFCE who have taken on the challenge of delivering such sessions of 3-4 talks by leading academic and industrial experts. You may know that EFCE is a scientific collaboration of many member societies representing about 100,000 chemical engineers in 30 countries all across Europe. And the working parties and sections, they are like the core, the heart of what makes EFCE, and they are the core and the heart of what makes chemical engineering in Europe. I would also like to take the opportunity to thank Hemptine and Ines, who've made this all possible and guided us through here, and who have stayed through all of these meetings. So they are now the best informed chemical engineers in all of Europe. And with that, I'd like to wish us all a very interesting and inspiring afternoon. Jean-Charles.
Thank you, Hermann. Thank you. So just a short introduction from the working party point of view. So I am Jean-Charles de Hemptine. I'm the working party chairman. And I want to just say a few words about what our working party is. It was founded in 2008, and the first president was Yannis Economou. The objectives of the working party are indicated here. Promoting activities on thermodynamic, transport, and physical properties, measurements, correlations, predictions, and simulations. We want to promote concerted educational activities in the area of thermodynamics and transport properties. We want to offer a forum to chemical engineers for exchange of ideas and coordinate research activities. Okay. The present chair, so that's me, Jean-Charles de Hemptine. We have two vice chairs, which are Sabine Enders and Susanna Kuitunen. So our typical activities are, well, awards that we deliver. Okay, an Excellence Award, which is an award for PhD students, and a Distinguished Lecture Award for senior member of the community. So each award is awarded once a year. We have an industrial survey that we published 10 years ago, and a new version is coming up soon. So this is one of the highlights also of our activities. We organize on a regular basis symposia, IUT, meaning industrial use of thermodynamics, which may be part of the EFCE meetings, or part of one of the community thermodynamics meeting, that is generally ASAT or thermo meetings. We have a number of education activities. We have a LinkedIn page, and we have a web page, the address of which you see on this slide. Among the awards winners, I may mention here Mona Martins. We should mention Gabi Sadowski, who got the award recently. Okay, these are a number of examples of actions we have. Let me just go to the further events for which I will make some more advertising at the end. We have a call for nomination for the Excellence Awards, and we have the ASAT meeting, the coming ASAT meeting in 2021. For which we have a call for paper that is now open. With this, I want to leave the word to Christof Held, who will be chairing this meeting. Christof, you should open your microphone. Yes.
So, hello also from my side. So, while sharing my screen, I welcome you all. Here I go. And yeah, it is quite interesting to have these series on EFCE Spotlight Talks. Some of you probably attended already some other Spotlight Talks, for example, in close connection to this one, the CCS and CCU. And we today have two talks, one of Maria Grazia and Angelis, one of Pascal Mougin. I will introduce both of them after a short introduction from my side. It will take 2 minutes. Why do we do this? So why did we decide to have this subject on CO2? Why? Because it's obvious climate change mitigation is among all of us, and yeah, we have developed tools to capture the CO2 that come from different sources and to utilize the CO2. Both technologies, so carbon capture sequestration, the gray one, and carbon utilization, the yellow one, they have two different ways of viewing them. So usually CCS is done when we secure energy provision or do not have much space, while we rather focus the carbon utilization when we really want to avoid fossil resources and support renewables. So we can also directly use it in greenhouses for enhanced oil recovery, or we can store it offshore. So, the techniques today we focus are on this gray box on carbon capture and sequestration. We have heard already in one of the Spotlight talks that it's possible to directly absorb the CO2 in these filters. Today we will have a closer look on membranes as well as on the absorption. And we will start with the membranes. I'm happy to introduce, and I'm happy to have her here, Maria Grazia de Angelis. She's Associate Professor and Degree Program Coordinator for Chemical Engineering in the University of Bologna, at least actually. And she told me that she thinks very important for her is that she's a member in the European Membrane Society Council and also of our Thermodynamics and Transport Properties Working Group that Jean-Charles introduced 5 minutes ago. And her interests, or her basic interests in thermodynamics and transport properties are polymer solutions, transport and polymer membranes, especially glassy material, CO2 capture, and equations of state. And the MVP in very down is the most valued paper in her opinion. So, and with this, I give the word to you, Maria Grazia, floor is yours.
Thank you. Thank you for a nice introduction. Let me share my screen. And we're in the presentation mode. And are you seeing it correctly?
Yes.
Yeah, looks good.
Okay, so I will. So thank you for giving me this opportunity of presenting my work and also the work of others from my groups and from collaborating groups. We will focus on the thermodynamic aspects of membranes for CO2 capture. And as Christof said, I'm a member of the Thermodynamic and Transport Properties Working Group, and I represent Italy. So I will first give a short introduction about membranes and how membranes work for CO2 capture in comparison to other conventional or more established technology, and we'll show you that membranes are considered a sustainable and compact choice. The standard membrane separation mechanism as far as polymeric membranes are concerned is the solution diffusion one, and I will show you the main aspects and its limitations. And I will focus on the two contributions that form this mechanism, which are the solubility, which is of course a thermodynamic quantity, whose impact on separation is often underrated. I will show you the main macroscopic approaches required to estimate and available to estimate solubility. Then I will switch to the kinetic contribution to the permeation and to the separation in membranes, which is the diffusivity. That is a kinetic quantity, but it also contains a hidden thermodynamic contribution on which, of course, thermodynamics can play a very strong role. And I will show you macroscopic approaches available now to predict the diffusivity and permeability. I will also show the case of a so-called facilitated transport membrane mechanism, a separation process in which simple diffusion is aided by a reaction, a chemical reaction taking place between CO2 and active groups present in the membrane. And I will show you the results of a simulation work that we are carrying out using the EPC Saft equation of state. Then I will give you a short overview of the main molecular approaches available to calculate solubility and diffusivity in membranes, and also very fast remarks on possible integration between the different approaches. And finally, I will draw the conclusions. So the reason why it is necessary to implement the CCUS in energy production and in industry is evident from what Christof said, but also from this chart that represents the trends, the future trends of CO2 emissions. And these are only the emissions related to energy production and utilization. As you see, the red line is where we're heading according to the predictions, and the green one is where we should go according to the Sustainable Development Goals. So it is now clear that reaching net zero emissions will be virtually impossible without applying CCUS to existing power and industrial plants. So possible applications are, of course, in the existing energy facilities, but also in industrial sectors such as the high energy intensive ones, like in the production of cement, of steel, and of chemicals. CO2 also can be removed efficiently during the production of hydrogen, because normally when hydrogen is produced, the CO2 is also produced. So if we want to switch to a hydrogen economy, we need to remove the CO2 produced together with hydrogen in many processes. And this can only be achieved through CCUS. Nowadays, it is also urgent to start removing CO2 directly from the atmosphere. And there are several technologies that are currently being tested for it. CCUS facilities were in a very big number at the beginning of this decade. There were many CCUS facilities in the world, and this number diminished and decreased towards the middle of the century, and it is increasing right now. So we can say that CCUS facilities are regaining momentum, and they are not only funded by public institutions and governments, but also by private companies like the oil and gas companies. The main CO2 capture technologies were already depicted by Christof. The membranes, compared to the most established solvent and sorbent technologies, are different in the fact that the membrane is a continuous process. The membrane does not require regeneration. It does not require heat. And also, membranes are normally resistant to the most aggressive contaminants present in flue gas or in other gaseous streams containing CO2. And the main disadvantage of membranes is that you can achieve a lower CO2 purity with this technology compared, for instance, to solvent absorption. The reduced footprint of membranes with respect to solvent columns, so absorption columns, is evident from this picture, where the green line represents a membrane system which treats 20 tons of CO2 per day. And in the white and in the yellow sections, you can see plants units which treat 20 and 10 tons per day of CO2 respectively, based on different types of solvents. So you can see that the plant footprint is very small in the case of membranes. Most CO2 separation membranes work in this way. They have a membrane which preferentially permeates CO2. You feed your feed stream, which can contain CO2 nitrogen or CO2 methane or CO2 and hydrogen, depending on the capture scheme that you are using. You compress this stream, and this is the main cost associated to membrane operations, the compression cost. And what you get is a low pressure permeate stream, which is enriched in CO2, and a CO2 depleted residual stream, which is still at high pressure. This occurs in the majority of the cases. So speaking about operative parameters, we have parameters which can increase the flux of CO2, which are related to process conditions, such as the pressure, which can, of course, be enhanced by compressing the upstream feed or by reducing the pressure of the downstream one. The gas fraction in the feed can only be increased by introducing recycling loops in the process configuration. On the membrane side, we have other parameters, which are the area, the permeability of the membrane, and the thickness. The membrane itself is a rather complex multi-layer system, which contains several layers that have different functions, such as protection or mechanical support. The active core of the membrane is the selective layer, which is very thin and which performs the separation. So with thermodynamics tools, we will try to see how to predict the material property, the permeability inside this selective layer. So by schematizing the permeation process in this way, we can recall the main physical laws governing this process. The flux is a purely diffusive one, so it's regulated by fixed law. And also you can introduce the permeability, which is the flux divided by the fugacity gradient. And there is also an equilibrium, a phase equilibrium at the interface between the membrane and the gas phase, which is governed by the solubility coefficient S. In the end, the permeability results as the product of diffusivity and the solubility coefficient. And the selectivity, which gives you the removal capacity of the membrane, also as a result can be decomposed as the product of a diffusivity-based and of a solubility-based contribution. In all membranes, you see a balance between the diffusivity-based contribution, which favors the smaller penetrants, and the solubility one, which usually, but not always, favors the larger penetrants. In the case of CO2, this mechanism is a little bit reversed, because CO2 is considered generally a small penetrance with respect to many other ones, but is normally highly soluble in polymers. In general, for rubbery and glassy polymers and high free volume glassy polymers, the solubility selectivity is can be equal or even more important than the diffusivity selectivity. Thermodynamics, of course, play a role in the solubility terms of permeability and of selectivity. It is also important to notice that most of the times membrane processes are designed using properties which are evaluated from experimental measurements carried out in pure gas conditions, while the real process involves mixtures, multi-component systems. So what you can see is that permeability, diffusivity, and solubility, and consequently also the selectivity, are different if calculated based on pure gas conditions or in mixed gas conditions. In particular, this is something that was published this year. If you take a look at the main glassy polymers used suitable for CO2 capture, you can see that if you consider only the pure gas data, it seems like membranes are dominated by diffusivity selectivity. While actually, if you go into detail and you take a look at the multi-component data evaluated on the same membranes, you see that the opposite is true, and the separation is mainly driven by sorption. And this again confirms the fact that solubility has a strong effect on the separation performance. What are the limits of polymeric membranes? If the size selected membranes are considered, we can observe an upper bound, which was first reported by Robson in 1991 and constantly updated with the discovery of new materials. The upper bound basically says that you cannot have a material which simultaneously shows high permeability and high selectivity. If you have high permeability, then it means that also the bigger penetrants will permeate, and so you will have a lower selectivity, and vice versa. There is a trade-off between permeability and selectivity, and an upper bound for the performance of the membranes. Let's now see how we can perform the solubility and diffusivity calculation and modeling. Solubility isotherms, solubility is normally reported in the form of solubility isotherms. You can see different behaviors depending on whether the membrane is a glassy or a rubbery one, and if you have an incondensable, if you have a light gas such as nitrogen or hydrogen, you will see a linear Henry's law type of solubility isotherm. At high pressure, you can see strange behaviors like changing slope changes of the solubility isotherms due to the fact that the fluid becomes supercritical. You can also see sigmoidal shaped isotherms in the case of alcohol absorption in glassy polymers. And you can also see a transition induced by the sorption of the penetrant from the glassy to the rubbery state during your experiment. The solubility coefficient is the ratio between the concentration and the fugacity, and you can have an infinite dilution value or an average value depending on which point you are focusing on the solubility isotherm. Luckily enough, we have several models available to predict or to correlate solubility, and in this slide I'm reporting only the empirical ones. You can of course use Henry's law with experimental data for the linear isotherms. You can use activity coefficient models for the rubbery polymers. For the glassy polymers, there is an empirical model which is called the dual mode sorption model, and is the sum basically of an Henry's law term and of a Langmuir term. There is no empirical model available to represent the behavior of sigmoidal or supercritical isotherms. More rigorous theoretical models are represented by equations of state, of course, and by a non-equilibrium version, which was provided valid for glassy polymers. This approach was presented in the 90s by Professor Doghieri and Sarti, and allows to account both for the solubility in the rubbery membrane, where you actually apply the phase equilibrium condition for the gas penetrant between the membrane and the external gas phase, and you simultaneously solve the equation of state for the gas polymer mixture, which allow you in the end to simultaneously find the solubility and the density of the polymeric mixtures. If you're working below the glass transition, the equation of state can no longer be used, but you don't have to throw everything you have, because you can still use your equation of state model to calculate the potential of the glassy membrane. of the gas polymer absorbed in the glassy membrane according to the derivation provided in 1996, first with the NELF model and then with the more general net GP model. In this case, you can still apply the phase equilibrium between the membrane and the gas phase, but the density has to be provided by correlations or by experiments, because the density of the glassy phase does not correspond to the equilibrium value calculated from an equation of state. You can rely on different equation of state, and you can apply this same framework, this same approach, using different available equation of state. The most suitable to the case of polymers are the lattice fluid one, the perturbed hard sphere chain, and all the equations of state based on the statistical associated fluid theory. They, of course, use a different representation of the substances. One uses the lattice, the other ones use a chain of spheres. They contain a minimum number of parameters equal to 3. The soft one also accounts for association interactions, and in that case, you have to add other parameters. Some results of the non-equilibrium lattice fluid modeling is reported here in comparison to experimental data. Here, the solubility isotherms of CO2 and methane are calculated for different composition of the gas mixture and allow to represent, the model allows to represent very well the data at all gas mixture composition, and in particular highlights the effect that methane solubility is very much reduced by the presence of CO2 in the gas mixtures, while the CO2 solubility is almost unaffected. This causes a reduction in the multi-component solubility selectivity with respect to the ideal case, the ideal value calculated based on pure component values. And another example of a similar problem is reported here. We are considering here a different polymer, matrimide, which is used in CO2 methane separations, and we are using a different equation of state framework, the PC soft. Again, we are able to understand the competition effect, which only occurs during real multi-component simulations, which cannot be caught assuming an ideal behavior based on pure gas values of the solubility. This is something which is actually reported also experimentally. Another story is the diffusion coefficient. First of all, we have to distinguish between the mutual and the self-diffusion coefficient, which also go under the name of mobility. The first one is the most common form of diffusion coefficient, is the one that appears in Fick's law and relates the diffusive flux to the concentration gradient, which is a very convenient quantity to be measured. Actually, the true driving force for diffusion in the membrane is not the concentration gradient, but is rather a chemical potential gradient. So if we rewrite an equation similar to Fick's equation, but using the chemical potential gradient instead of the concentration gradient, we have a different physicochemical parameter that goes under the name of mobility. This is the one relating the flux to the potential gradient. After a few manipulations of these two equations, we can then see that the mutual diffusion coefficient can be seen as the ratio between a pure mobility, which is the self-diffusion coefficient, and the thermodynamic factor, which is actually dependent on the shape of the solubility isotherm, and that can be calculated with one of the models that we just saw for the prediction of the solubility. And for instance, if we use the Flory-Huggins model, the thermodynamic factor alpha can be readily evaluated. Note, please, that the self and the mutual diffusion coefficient coincide if we are in pure fluids, of course, or if we are at infinite dilution. These concepts were combined to the tools for the calculation of solubility by Minelli and Sarti, who developed a unified approach that goes under the name of standard transport model that allows to simulate both the solubility and the diffusivity within the same framework. In particular, they used the non-equilibrium model to find the solubility contribution to the permeation and the solubility, the thermodynamic factor in the diffusion coefficient. And they used an empirical law based on the free volume theory by Rentas and Duda for estimating the mobility. And finally, they found a unique expression for the permeability as a function of the pressure on the downstream and upstream sides of the membranes. This theory contains two adjustable parameters that are L0 and beta. And the model performs very well because from the parameters obtained from the modeling of absorption isotherm, you can easily estimate accurately the trend of CO2 permeability in the same polymer, which in this case is polycarbonate at 35 degrees. And the model can also predict the presence and occurrence of a plasticization pressure, which has to be avoided during membrane separation processes because it leads to a loss in performance. Another example that I promised you to show was the example of the facilitated transport membranes. And as I anticipated, in this case, besides diffusion, you have a chemical reaction that takes place between CO2, the water that is present in the environment, which is humidified, and aminic groups present in the membrane. There is the formation of an ion which diffuses fast and which boosts the permeation of CO2 with respect to the permeation of all other gases. This mechanism allows to surpass the upper bound observed by Robson, and so it is very much studied, and it is actually under study now for CO2 capture processes. You can actually use a thermodynamic model to model the absorption with reaction, and this was carried out in the framework of a European project just concluded, and the model used was the polyelectrolyte Feise equation of state, and the polymer studied was polyvinyl amine, which is a polyelectrolyte. So this model uses the same scheme valid for the Feise equation, so associative interactions, dispersive interaction, and so on, plus a term accounting also for the ion interactions. The hydrogen bonding term, of course, is related to the presence of associating species, self or induced associating species such as water, CO2, and the polymer, and the ion term is associated to the presence of the diffusing ion and of the ions attached, the aminic ones attached on the polymer backbone. So this is the scheme of the reaction that takes place in the polymer, and these are some results. Unfortunately, we do not have experimental data for the enhanced absorption of CO2 in a humid polyvinylamine, but you can correctly see the trends and correctly understand what is the pressure of CO2 required to have a certain fixed CO2 uptake in the membrane at each value of the temperature and at each value of the relative humidity of the membrane. As I told you, we do not have experimental data on absorption, but we tested this same approach not on a polymer membrane, but on a liquid system, in particular on systems formed by water and MDEA, for which there are many experimental data. And the same model works well in predicting the data. Of course, the accuracy between the model prediction and the data becomes, the comparison becomes worse in the case of solutions contain a higher amount of aminic component, which is of course more challenging for the model. But in the case of a lower amount of MDEA, we have a good prediction of the model, of the absorption curves by the model. Okay, let's give a look also at the molecular approaches in these last minutes. And I am actually pointing you to a very nice review that was published last year by the group of Professor Teodoro and Niki Vergado, which gives you an update on the efforts carried out in the last 2 decades about molecular simulations of polymeric structures, sorption and diffusion. You have different methods available with different levels of computational efficiency and of accuracy. Molecular dynamics, of course, is the most standard one. Monte Carlo is a bit more system specific, although it allows you, especially in polymeric systems, to cut the computational cost of the methodology. Also, the prediction of diffusion can be carried out not only with the classical Einstein's equation, but also using other methods which allow you to cut the computational effort, such as the transition state theory or path sampling. As far as the mesoscopic techniques are concerned, you can apply coarse graining methodology, so you can group the atoms and renounce to an atomistic view of the system and also renounce to some detail, but in this way you can speed up a lot your simulation. Solubility can be predicted using the test particle insertion method, such as those invented by Whedon. And in particular, there is a slide here that shows you how to calculate this solubility with molecular techniques. You can insert a test particle and calculate what is the interaction energy between the particle and the surroundings. And this is directly related to the solubility. If you are at infinite dilution, you insert the molecule into a pure polymer. And this is a very easy calculation. If you are at higher pressure, you have to insert your CO2 molecule into a polymer loaded already with CO2 molecules. And this is, of course, necessary to predict solubility isotherm. And in this case, you have to apply an iterative scheme to exactly match the external gas pressure with the equilibrium amount of CO2 in the membrane. But the convergence is reached after only 2 or 3 loops of the iteration. Einstein relation is the one normally used to predict the self-diffusivity, and of course, to predict the mutual diffusivity, you need a sorption isotherm, as we explained in the previous slides. The accuracy of these predictions in terms of solubility of diffusivity, especially in the glassy state, are still low compared to macroscopic techniques. Of course, you can integrate macroscopic with microscopic, and there are several efforts in this respect. For instance, you can parameterize, you can find the parameters for polymers suitable for the equation of state modeling from molecular dynamics. And this is what we did in the case of a polymer membrane for which no experimental data were available for parameterizing the PC-SAFT equation of state. So we performed high temperature molecular dynamics simulation. We found the parameters for the equation of state, and we later used those parameters at room temperature to predict the solubility. Another possible approach is the integration with machine learning methodologies. For instance, you can implement machine learning tools to find the best coarse graining strategy in molecular dynamics simulations. And there are also other possible interactions between machine learning tools and molecular dynamics, which can speed up a lot the simulations and make them less computationally intensive. So in conclusion, I would like to say that, of course, CO2 capture with membranes is a process which can be rigorously simulated using macroscopic models, which can help designing optimal membrane separation processes with few adjustable parameters. Also, the molecular approaches can provide an help, and however, in particular, they are very promising in simulating harsh operative conditions, which cannot be reached experimentally, and also in the design of new materials and in the estimation of new materials. But the accuracy is still lower compared to the macroscopic tools, and also we need to reduce the computational weight of these methods. However, the predictive power is very, very, very high, because you only need the molecular structure of the material, and then you can predict almost everything. So ideally, one should find the optimal solution currently in the integration between the different approaches. Okay, with this, I would like to conclude. I have not prepared an acknowledgement slide, because I displayed a picture of all the contributors to this work throughout my presentation. So I hope you enjoyed the presentation, and I will be happy to take your questions.
Well, excellent. Thanks very much, Maria Grazia. And we got a couple of questions. So I will start with the first question. The behavior where you showed the very strange behavior at very high pressures. Do you have a feeling at which pressures this starts? So is there
pressure, and the reason for this behavior is that okay, let me show this to you again. Okay, so here what you see is that the solubility isotherms around the critical pressure of CO2 flattens out. This is because the CO2 starts to behave in a liquid-like manner, and liquids are insensitive to pressure. So liquid properties become, the solubility here, the solubility of CO2 becomes less dependent on the pressure, because the behavior is a liquid-like behavior. So the curve flattens out.
Okay. Great. So then we have a second question from Susanna. She's asking through the chat panel whether or not the models that we have been now establishing for the last 10, 15, 20 years are ready to be optimized or utilized for optimization in industrial setups. What do you think?
Yeah, definitely. We have such powerful tools, for instance, the EPC software that I showed, of course. You need to work a little bit on them, because you need to accurately find the correct scheme. For instance, the higher the degrees of freedom of the approach, like in the soft case, you have to choose the association scheme. If you have ions, you have additional parameters to account for the ions. So you need some setup at the beginning, which takes some time to choose the accurate the right parameters and the right scheme. But once that is done, the tools are there and they are very powerful.
Yes, I agree. Maybe sometimes a little bit slow models, though, especially those advanced models, but yeah, but maybe we need surrogate models to use them. But yeah, I have the same opinion. One other question is addressed on the swelling behavior. So does this need to be taken into account?
Yes, it does. Because especially if you're dealing with CO2, and if you're dealing with CO2 at high pressure, the swelling is relevant. And in the case of a rubbery polymer, you can rely on the equation of state for you to provide you the correct value of density. But if you are below the glass transition, there is no way to estimate a priori the density. And because the system is no longer following the equilibrium path, it's no longer following what is dictated by the equation of state. So in that case, you can rely on, for instance, this equation reported here, based on which the density is a linear function of the gas pressure, the polymer density. So this is based on experimental observation that tell you that the density of the polymer decreases with increasing gas pressure. And this approximate behavior is consistent with reality in several cases. So based on this law, you just need one swelling coefficient that gives you the slope of the density with the pressure to perform the simulation. But indeed, it is a datum that needs to be provided to the solubility model for having a correct estimate of the solubility at high pressure.
Yes. Okay, thanks for that. And then there is a question from Akshay Patil, whether you know or work together with companies that really use polymeric membranes for CO2 capture.
Yeah, there are companies in Europe, for instance, Evonik, which produces membranes for biogas purification, which is a CO2 mass and separation. They produce hollow fiber membranes. There is Fujifilm that also is developing membranes for natural gas, but also gas purifications. These are the first ones that come to my mind, but of course there are also other ones. The membrane technology now is very much established commercially in water treatment. In gas purification is a bit less developed, but I'm sure that the CO2 capture needs will speed up a lot the scaling up of this technology, because the cost of the membranes will be reduced and also there will be more solutions and options available for people that actually want to implement CO2 capture with membranes.
Yeah, totally correct. So this is a trade-off. And maybe a question which comes from Maurizio Famiglia. So connected to this, about the dimension of the CO2 capture plants, whether or not you have an idea of how the dimensions are of such a plant, considering the fact that the flow rate of a flue gas of a power generation plant can be really, really high.
This is
so maybe more than 50 tons per hour. So what about the dimension of such a...
Well, in the end, it depends on the packing density. So you can play on the packing density. You can have different geometries of the modules. The hollow fiber modules are the ones that have the highest packing density, so the highest surface area per volume of the module. But they also offer higher. They also have higher pressure drops, pressure loss due to friction. So there is a balance, of course, between pressure loss and packing density. But the size of the membrane system is a modular system. So you can have, you can simply multiply the number of modules. You can add modules, and you can treat a larger flow rate. When I asked this question to a person that works in a membrane company, he told me we can potentially reach millions of square meters of membrane area, because this is what they do when in desalination plants, in reverse osmosis desalination plants. So when they tell that membrane-based CO2 capture cannot be applied because you need a tremendously high surface area of membranes, you should think about desalination plants, which also require a very large membrane area, but they are a reality.
Yes. Then the last question before we move on is whether or not it might be possible to remove completely the acid gas by membrane technology?
It is difficult unless you remove completely with membranes. Is difficult. This is the technology that gives you, at least in one single stage, the lowest purity compared to solvent systems, for instance. So with one single step, it's impossible to completely remove, to have 100% removal, or the question was about the removal or about the purity of?
No, about the removal.
Removal. Normally, the target is initially, when at the beginning of this decade, the target was 90% removal of CO2, which was achievable. But then the target starts to go down a little bit. So people started thinking that maybe also partial capture, like 70% CO2 removal was acceptable in certain circumstances. And actually membranes are very good and very cost effective when you lower a little bit the target and you want to achieve partial capture.
Yeah. So maybe let's conclude with that. In my mind, also this question is a nice to go to the next presentation, because with absorption we can really go to very, very, very low partial pressures of the soil gases, right? So Maria Grazia, thanks again for all these answers, and by this let me just briefly introduce the next speaker. It is, oops, that is certainly the wrong slide. It is Pascal Mougin. Pascal is actually head of the thermodynamic and molecular simulation at IFPEN Energie Nouvelle, and he thinks that his very important steps on his career was to include rules from thermodynamics and transport properties in more than 50 processes within IFPEN Energie Nouvelle. He's also interested in CO2 capture, gas treatment processes, PVT, and also on thermodynamic modeling and equation of state. And very down you can read again the most valued paper that he thinks he has contributed to. And with this, I give the floor to you, Pascal. Please go ahead.
Thank you. I think, I hope that, yes, it's work. Just I think that you will see my screen. It's okay?
Not yet.
Not?
Ah, now
Yeah,
Yeah,
yes.
That's coming.
much better.
it's coming. Yeah. Okay, so hopla. Yes, let's go.
Yeah, perfect.
Thank you. So thank you, Christof, for these introductions, and good afternoon to all of us. So I saw here discuss about thermodynamics approaches for demixing solvent in the context of CO2 captures. So yes, just 2 slides about IFPEN. Who are we? So IFPEN is a public sector research and innovation body with about 1,600 people. IFPEN is also a training center, and it's industrial groups, and it's the field about energy, transport, and environment. So this is and our missions is integrated into the context of climate change and energy transitions. So there are many challenges. You can see here some about the mobilities, diversifying energy sources, increase the energy efficiency, improve the availability of and the use of fossil resources. This is some challenges IFP has given itself. And these changes has focus on the area of three main priorities, which is research and innovations, training, and value creations. So now we can back to the CO2 capture problematics. So I show you a graph that I know that there are plenty of this graph in literature. So this is the increase of the temperature during the last centuries. We will see that there's a large growth of the temperature, and for this year is not finished, but it should be one of the third greatest temperature effect for the last century again. So the problems about these tendencies is mainly due to the human expansion of the greenhouse effect. And so about this greenhouse effect, we have focus on this component, which is water molecules, nitric oxide, methane also, and carbon dioxide. And if you are looking about the proportion of greenhouse gas, carbon dioxide is focused mainly about 75% of the emissions. So another well-known graph is the CO2 content in the atmosphere. So we can see that for the last billion of years, so the CO2 levels has increased now in the last decades, and that we have never seen high levels during the last billion of years. So this is a problems, and we need to reduce the emission of CO2, and we need to avoid to break this increase of CO2 content in the atmosphere. There are mainly three ways in order to do the CO2 captures. So the first one is about the pre-combustion. So the combustible is submit gasifications and a shift conversion in order to obtain CO2 and hydrogen. So it's an extraction which is very easy to perform, and so after we can burn air and hydrogen in order to do the combustion, so to obtain the energy. And in this case, the CO2 is easily removed. Another way is oxycombustion. So here, from the air, we do a separation between oxygen and nitrogen, and so we do the combustion directly with pure oxygen. So we obtain, as with the flux, we obtain CO2 and water. The condensation separate easily both products, and there are no main problems. So these two process is a new one and need new units to be efficient. A third process, which is more conventional and more easily to use for existing process, is the post-combustion. So here you do the combustions with air, and then we do a pretreatment and extraction of CO2 from nitrogen, water, oxygen, and so on. And so we obtain the CO2 that we can reinject, for example. So in this case, we can use solvent, adsorption, membrane, as Maria showed before, hydrate, and so on. There's many ways to do these extractions. So in this case, I will focus my topics about the solvent. This is a classical post-combustion capture process. So this kind of process should be used in existing plant in order to reduce, to avoid the CO2 emissions. So the flux goes to a first tower in order to separate some impurities, and then goes to an adsorber. And so the CO2 flux is in contact with an amine, a solvent, which is start at the bottom. And when at the top here, we obtain the purified gas, and at the bottom here, we obtain the rich amine, so solution of amine with CO2 product and CO2 unique species. This amine goes to an heater and goes to a stripper at high temperature, and so we can separate the CO2, which can go to a compressor in order to be rejected, for example. And at the bottom, we obtain a line amine here, which can be recycled to the tops of the adsorber. The cost of the unit is mainly due to the duty of the boiler, the stripper here, which is compared to the heat of vaporization of a solvent, the heat necessary to reverse chemical reactions, and the heat to increase the temperature of the solvent. So this is the three main part of the duty for this stripper. On this graph, you can see the evolution of the duty of the process during the last 30 years. So starting, the blue diamonds is about the MEA, which is the monoethanolamine process, which is the more conventional ones. So we can see that at the beginning of the 19, the cost of CO2 capture is about 4 gigajoule per ton of CO2. And improving the efficiency of the process, improving the description of the kinetics, and controlling the hydrodynamics of the process of absorptions, we can reduce the duty to a value about 3.5 gigajoule. Then, at the beginning of the 20s, we have this new solvent with as a target about 3.0 gigajoule by ton of CO2. And then, at the beginning of 2010, IFPEN proposed a new solvent with a demixing process, and the objective is to reduce the cost of the duty to about between 2 and 2.5 gigajoule by ton of CO2. The demix process is the following. So it's very close to the classical ones, but here, after the heat exchangers, you will have a demixing of the phase at the outlet of the chiller. So we have two phases: a heavy phase with a large amount of CO2, and light phase, which is rich on amine solutions. So we put on the process a decanter, and so the light phase goes directly to the adsorber, and we reinject the heavy phase to the stripper. So this is in this situation, the stripper is focused only on the part of the amine which are reactive with the CO2. So to simulate all this process, we need information about thermodynamics, the kinetics of the absorptions, the hydrodynamics also, and also some information about the coercion of the solutions, the degradations of the solutions as a function of temperature, and about the presence of impurities, and also some information about the operational issue. So in these topics, I will focus only on the thermodynamic part of the development. So the development workflow of the thermodynamic models is the following. So we start from the data, from the open literature and internal data, in order to build an experimental database from different properties, the thermophysical properties, and we use this data in order with some theoretical framework, such as group contribution methods, equation of state, activity models, or semi-empirical or empirical correlations, in order to propose a model for the process. And in fact, all the developed models are integrated into process simulators. So we are looking mainly on two sets of thermophysical properties. The first one is about phase equilibrium and enthalpy in order to propose mass and energy balances. And the second one is about density and viscosity for the design of units. Alors, the main part of the process to calculate to establish the process is the phase equilibrium, and in this case, the phase equilibrium is a coupling between physical equilibrium and chemical reactions. So you have a system composed by water, amine, CO2, and impurities. So this process, this component is present in the vapor phase and are in a physical equilibrium with the same component in the liquid phase. And in the aqueous phase, so amine react with CO2 in order to promote carbamate, protonated amine, and carbonate, and so on. So it is necessary to couple both set of equations in order to take into account the effect of reactive equilibrium on the physical ones. And there is also a link between the phase equilibrium and the enthalpy of the solution, because the absorption of CO2 in a mine is a very exothermic effect. So the relationship is given by the derivative of the partial pressure of acid gas as a function of temperature. So the first step in order to propose a thermodynamic model for these systems is the need of experimental data. So we need isotherm of absorptions. So this isotherm of absorption is well documented for conventional alkylamine, MEA, DA, MDA, piperazine, and so on, but very few data for new amine. So we need to go to the labs in order to obtain new data for new component. This isotherm of absorptions is needed in order to sizing the capacity of the unit and to precise the operation conditions. We also need some correct calorimetric measurement, so for the duty of regeneration of the heat exchangers, and an improvement should be the speciation in the aqueous phase in order to know exactly the composition of the all unique species. And this is needed if we would like to propose after a kinetics of CO2 absorptions. Alors, there is here some experimental apparatus for obtain this data. This is an example here of the static cells for VLE data acquisitions. So in above, you have here an equilibrium cells where you can put a solvent, and you can add gradually CO2 amount into the cells. So you keep the temperature constant, and as you increase the number of mole of CO2 in the cells, you can do a measurement of the CO2 pressure in equilibrium. So this cells has a TP probe, and also it is possible to add a sample device in order to analyze, for example, the vapor phase with gas chromatography. So in this equipment, we have some calibrated gas reserves, so we can know exactly, we have access to the quantity of gas transferred from the reserves into the equilibrium cells. And then in the equilibrium cells, we do measurement of the temperature and pressure. And so using mass and density balances, we can access to the partial acid pressure as a function of the composition of a liquid phase. We can also add some analytic composition with analysis of the vapor or the liquid phase. On this graph, you have typical data from this equipment. This is about each trace. Each trace should be an impurities of a process. So you can have here the partial pressure of each trace as a function of acid gas loading. The acid gas loading is defined as the contents of acid gas divided by the amine amount. And so you can see here a good agreement between the data obtained on this equipment and the data from the literature. And you can see also that we have, for this kind of systems, five or six power decade for the pressure, which is due to the presence of reactive systems. So we can have very low pressure and very high pressure in the same systems. So this is a difficulty in order to model this kind of systems. Second type of data measurement is about the heat of absorption. So the purpose of the measurement is the same as previous ones. So we have a cells where the solvent is added, and so we adjust some quantity of sour gas, and we do the measurement of the heat released. And so we can obtain the quantity of heat of absorption as a function of the quantity of CO2 absorbed. So this is here a thermograph, and here you will have the calorimeters and all the line necessary to introduce the CO2 into the calorimeter. The third equipment is about the specifications, which is important also. So this is cells, for example, here. So we have also an introduction of CO2, and in these cells we have a piston, so we can adjust the pressure, and we have here infrared probe in order to do spectroscopic analysis. And so we had some increasing amount of CO2, we can see the modification of some peak that we can relate it to some specific ionic species. For example, here you will have a peak when you increase the CO2 loadings, so we have a peak which is specific for the carbamate, and you also identify some one in other area of spectroscopy diagrams. So after calibrations, you can perform such data as the concentration of ionic species or molecular ones as a function of CO2 loadings. And so you can see here the decrease of MEA and the increase of MEA plus or carbamate or bicarbonate. So all this data should be used after for the modeling, and this is the part that I'll show now. Just do a mistakes. I'm forget the three-phase cells, which is important for the DMX solvent. So this is another equipment, so static cells, where we can do sample on each liquid phase and do the analysis of each phase. So the analysis performed on the water contents, for example, by coefficient measurement, and also the measurement of amine by gas chromatography and CO2 by acid-base titrations. So we can obtain the, the analysis of the two liquid phase, and so obtain for each phase the loading of the phase and the amine contents, and then mix all these informations with liquid vapor or pseudo-liquid vapor partial pressure, and so we can produce three-phase data for the modeling. For this modeling, we think that the phase equilibrium is a coupling between chemical and physical behaviors. So there are two main ways to calculate the chemical reactions. The first one is the stoichiometric patterns, and use the mass balances and the chemical potential of each component. So if you write the mass balances and with the chemical reactions, you obtain the mass action law. And so the solution of the mass action law gives the composition at equilibrium. So this is the stoichiometric patterns, and it should be very efficiency way. But we need to have a specific development for each topic, for each set of reactions. If we would like to have more general approaches, we can do a second way, the non-stoichiometric patterns, which is based on the Gibbs free energy minimizations. So we calculate the Gibbs free energy from the chemical potential of each component. We have also the mass balances as a constraint, and we can obtain the composition at equilibrium if we obtain the real free minimizations of the Gibbs energy. This procedure is more general, is very useful, but we need a very complex and very efficiency algorithm of minimizations in order to avoid any local minimization. The main properties for the calculation of a phase equilibrium is the chemical potentials. So it has a classical divided in two terms, the reference term and the mixing terms. So for the reference terms, we use acid-base measurement, so to the pKa, in order to obtain expression of pKa as a function of temperature, and you can tabulate in a different way. So we obtain the chemical potential at infinite dilution in water. If needed, if we are use the calculation using equation of state framework, we need to do some calculation to change the reference state. but it's not the main problem for this kind of reference term. The main problem about it comes from some product, and in particular the carbamate composed by CO2 and amine, which is not stable, and so the product cannot be isolated, and the measurement is not possible. So these parameters becomes an adjustable parameter. So this is a major inconvenience of the systems. For the mixing terms, so we can use homogeneous approaches. So for example, we can use an electrolyte equation of state for all species, molecular and ionic species. And so, for example, if we express the Helmholtz energy, so we can divide the Helmholtz energy with three main terms. The first terms is the classical physical interactions, and it comes from SRK equation of state or Penn and Robinson, or it can come from Saft equations. The second terms needed from the ionic species is the electrostatic terms. So we can use MSC terms or Debye-Huckel. And we can add another terms, which is the Born terms, in order to take into account the difference between the dielectric constant from the reference, which is the water, and the solvent. So this is two terms that we can include for the electrostatic contributions, and the last contributions is the short-range interaction between ionic species and solvent. So there are many ways and many proposals in the literature. This is two examples. So this is semi-empirical contributions in this case, and there are also some development using the associating terms of the perturbation theory in order to take into account this short interaction between ionic species and solvent. Now, this is a first way to model the liquid phase. There are also another way, which is using also equation of state. In this case, with two terms, without any consideration of electrolyte species. We work only on apparent species, so water, amine, and CO2, for example. And so we find the classical part of the Saft equation, for example, or CPA, and the associative terms only. And chemical reaction is treated as a strong associating interactions. And so the chemical reactions is formulated by these terms. In these formulations, we do not use the chemical reactions. The chemical reactions is integrated into the associative terms. This is the second way to calculate the chemical potential. The last one is using an heterogeneous approach with the equation of state for the vapor phase, so Penn, Robinson, Soave, Ulrich-Kong, and so on, and activity models for all species in the liquid phase. In this case, the Gibbs free energy of the liquid is should be divided in two contributions: short-range interactions. So we can use virial equations or local composition. In this case, here you will have the extension of electrolyte NRTL models. So this is for short-range interactions. And for the long-range interactions, we find again the electronic terms with the MSC or the Debye-Huckel terms, and again the Born terms, which gives the effect on the dielectric constant. Alors, for industrial point of view, activity models are mainly used, in particular ENRTL. ENRTL is available in many process engineer simulators, and so is very used. Alternative way is the electrolyte EOS, for example, electrolyte CPA or electrolyte SAFT. And Maria Grazia has shown some result about electrolyte SAFT previously. So this is a new way to obtain this the modeling of this phase, the phase equilibrium. The problem with all these models that there are a lot of component. We have major component and traces, and we have also a lot of interactions, and so a lot of parameters. And we need to do sensitivity studies in order to define the main interaction between species and to define which are the main interaction to be calibrated, to be optimized. It's important to, when we have defined the main interactions, to fit to optimize the parameters using VLE and enthalpy data simultaneously. This is a real improvement, and we can obtain, if we consider some data coming from different ways, the mean deviations about 10 to 12% on isothermal data and 10% of enthalpy data. This mean deviation should be considered as higher, but the system is very difficult to modelize. There are very low partial pressure, very low pressure at to less than 0.05 millibars, so it's very difficult to access to these quantities. And we have also very high pressure, so it's difficult to cover all the range of the pressure with the same set of models. So this explains these mean deviations. And then to obtain these deviations, these models, we can check the quality of the models on the specifications, if needed, if available. Excuse me. There is here some example about the result of NRTL models. So, for example, here you have the fugacity of partial pressure of CO2 as a function of CO2 loadings for MEA solutions. You have here the effect of the temperature. So in the symbol are the experimental data, and the line has the models. So you can see that we can reproduce well the data for this large area of pressure.
Pascal, the time is already almost over. So can you finish within the next 2 to 3 minutes?
Yeah. So this is another example about heat of absorption. So this is so we can see that the effect of different amine, so more basic amine or so less basic amine, and we can see the effect if we are carbamate or not carbamate, if amine is primary or secondary amine of its ternary amines. So all this information about the reactive of amine should be taken into account. And on this, also with the same kind of models, we can also obtain a good description of the compositions of the liquid phase. The main part about liquid modeling, which is important on these topics. These two graphs is to show you the difficulty that we can have for this kind of system. For example, water and two piperidine, the N-methylpiperidine and two methylpiperidines. So we can see that they are not very main difference between the two molecules, but we have many very different way. When if we had some CO2, for example, in this case, with CO2, we decrease the temperature of the mixing. In this case, we increase the temperature. And in this case, we reduce the size of composition range. And in this case, we increase these situations. So we can see that the behavior is very difficult to capture and it's very difficult to model. So for the moment, for all the process developed for including liquid-liquid modeling, based liquid-liquid system calculation on semi-empirical modeling. But the target is to assume more rigorous thermodynamic modelings. So using the same models for calculate liquid vapor and liquid-liquid equilibrium. And so we need more developments. So need to improve the reactive flash calculation in order to go through VLE calculation to VLLE calculations, and it can be performed using minimization of Gibbs-free energy. We have in the department, we have still some people in charge of this kind of calculations, and we need also improvement of optimization method in order to be more robust and efficient, to avoid any local minimums, and also to have a good strategy to select the best parameters to optimize. So in conclusion, so it's possible to develop a new solvent for CO2 capture. It's possible to capture all the information about thermodynamics and to obtain a good quantity of thermodynamic models for process engineer after. But we need some needs for carry on the effect. We need new measurement for calculation, new solvent, and so the labs is still needed. We also have the modeling with VLE, with activity models or electrolyte equation of states. So there are development, and we need still deep development. And for the VLE situations, the improvement should be carried on reactive system, flash and optimization methods. So this is finished. Excuse me for the speeding my hand. And but Jean-Charles has already said that we will have ESAT 2021 in July in Paris. So don't forget to submit your abstract before the end of January. Thank you.
Very, very, very nice. So that was an excellent overview. Thanks, Pascal. The first one's coming from Claudio Madedu. Is there already any industrial application for the phase change solvent?
For the moment, there's no main industrial applications. However, we have started a new pilot in Dunkerque, in the north of France. So starting not in next years, but I think it's in 23, a new pilot with a demixing solvent will be performed. Yeah.
Very nice. And then there is a question on the accuracy of the models. So what's your feeling? In non-reactive systems, we usually have like deviations between data and modeling of maximum 5%. Yeah. And now you told us that it is minimum 10 to 12%. Was that on pressure? And is that an expected deviation?
This is the deviation in pressure is there are two main problems. The first one is if we use a large amount of data coming from different labs, there are some deviation between experimental data because there are many different way in order to obtain the measurement. So the data themselves has some deviations, and after we have the accuracy of the models because we need models with a large scale of pressure. If we are looking about minus 10 minus 5 bar, it's difficult to obtain very strong accuracy. So this is the mix of the chemical systems. It's very difficult to models, and the data themselves are difficult to obtain.
Yes, I totally agree. So then there is another question, whether or not it is possible with the experimental device to catch also the kinetics of the absorption. Do you do this?
Yeah, it's not we have for the development of a process, we have performed also some kinetics measurement in our cells, in our equipment, in order to design the size of the absorber. Yeah.
Okay. And those thermodynamic models, do they also contribute to model kinetics?
Yeah. Yeah, there's the thermodynamics is the base and gives the equilibrium, and so is used as an input of the kinetics.
Okay, I see. I was wondering myself, in the model you showed some short-range interactions, some special short-range interactions which you explicitly accounted for between ion and solvent. Usually, so that's what I understood so far, is that is already always incorporated also in the classical physical part. So isn't that doubled then, if you have an extra contribution for the ion solvation?
Yes, it depends. In this case, I show you the different way. In house models, we use heterogeneous approach with activity models, and in this case, the interaction is between ionic species and solvent only. So this is it's more after the main contribution is difficult to access, and for the development of equation of state for electrolyte is still an open question, and there are many solutions in the literature, and we need also research about these systems. But yes. I said, Michael said, time is too short for electrolyte.
Yeah, totally agree. Yeah. So with some words from Susanna, I will close this. She says, thanks for this interesting presentation, and it's so important that we have a robust model parameter optimization, and very good that you're developing such methods. I totally agree. Thanks again to you, Pascal. Thanks again to you, Maria Grazia, and I give the final word back to Jean-Charles.
Yes, thank you, Christof. Pascal, if you can leave me the screen so I can just re-show my final slide. But you saw it earlier anyhow, and Pascal also mentioned it. So I just wanted to finish with these two calls, I would say, from the Thermodynamics Working Party. There are two calls open at the moment. One, which is a call for nomination for the 2021 Excellence Award. So this is for the best PhD thesis. So please don't hesitate if you have good students to submit your nomination. Generally, it's really a very exciting period to listen and to give so this award. There are very nice works being done in European universities on this. The second call is the same as the one Pascal just mentioned. So you have noticed that the ESA 2020 has become ESA 2021, and that there is a new call for paper that is being open until January 31st. So please feel free to submit any paper. CO2 is of course one of the main topics. And more generally, I would also say we want to focus also very much on this issue of electrolyte thermodynamics. That Christof is one of the main actors in this field in Europe. But this is really a topic that people need to work on. There are still lots of open questions. Life is too short for electrolytes. So thank you for everybody to have attended this webinar, and hopefully we will see you in Paris in July, hopefully in person. This is not decided yet, but this would be very nice to see you there. Thank you.